All right, class, let's review the remainder theorem. Let's first of all begin with a third degree polynomial, and I'm going to call this polynomial right here f of x. Okay, so what I have is f of x being divided by x minus 2. This is a first degree divisor, okay, and that is our dividend. Okay, now, I know because this is a first degree polynomial with a leading coefficient of 1, I know that I could do this using synthetic division, okay? And we can identify what r is. R is the number 2, I'll highlight it in red. So, r, which is 2, is the number that is being subtracted from x, right? And so in here, I'm going to put the coefficients of my dividend. All right, and then we're going to perform the synthetic division. So multiply diagonally, add vertically. Okay, 2 times 4 is 8. 10, multiply diagonally, I get 20. And then I get a 21. Okay. So double check those numbers. All right, looks good. Okay, now we have the division algorithm, which says that this dividend, f of x, okay, which is 3x to the third minus 2x squared plus 2x plus 1, can then be represented in terms of the what? In terms of the quotient, right? We can take the quotient, which is 3x squared plus 4x plus 10, and then we can now multiply that by the divisor. The divisor was x minus 2, okay? And then we can add the 21, which was the remainder, okay? So remember, the f of x was the dividend, and the division algorithm said that the dividend could be represented in terms of the quotient, okay, which then gets multiplied by the divisor, and then we're going to add the remainder, okay, REM for short. Okay. Now, when you plug numbers into this function, we see that those numbers can go into here, okay, and we can get our outputs that way, but we can also plug in x's, and you can see that they could then go into here, and into there, and also into there, okay? So, look what happens if I take my function f, and I now plug in the r value, which was 2. Well, that 2, if I follow the red path, that 2 is going to go into here and there, and notice you're going to get some number, right? It's going to be 3 times 2 squared plus 4 times the 2 in red plus the 10. But notice, who cares what all this is going to equal? Because that 2 in red is also going to be placed right here. And now I'm going to have 2 minus 2 plus 21. And now you're going to end up with a big 0 here, okay? And 0 times any number will make all of this become 0, and your output will just equal 21, okay? So, plugging in 2 into the dividend here, the polynomial up above, gave us an output of 21, okay? So what it shows us, what this is showing us, is that f of 2, which is equal to 21, was simply equal to the remainder of f of x divided by x minus 2. Okay? And that is what the remainder theorem tells us. Okay? The remainder theorem, and I'm going to write it for us in a moment, it simply says that we're going to be able to find function values for our polynomial, or or in other words, we're going to be able to find range values, outputs, for our polynomial by performing synthetic division. Okay? So let's go ahead now and formally write the remainder theorem. Okay, so the remainder theorem says that we're going to begin and we're going to let f of x be an nth degree polynomial. Okay, so if the polynomial f of x is divided by a first degree polynomial called x minus r, then the remainder of that division, is equal to the function f evaluated at that number r in red. Okay? Now, we can also turn this statement around. Okay? We could say that f of r, okay, is equal to the remainder of our polynomial f of x divided by the first degree polynomial x minus r. Okay? So here, let me take the second statement and say that f of r is equal to the remainder of f divided by x minus r. Okay? So this is what we want to focus on. Okay? So when you plug numbers into a polynomial function, we're going to want the outputs. And the outputs will be computed by performing a synthetic division. A synthetic division between our polynomial f and x minus r. Okay? So let's do an example. Let's say that we're given a polynomial f of x. And let's make one up. Let's say I've got x to the third minus 4x squared plus x plus 6. Okay? And let's say that I now ask you to find a function value. Let's say that I ask you to plug in -2. Okay? Now remember, when we did this the good old-fashioned way, we just plugged in the -2 into here, there, and there. And let's do it the old-fashioned way. Take -2 to the third minus 4 times -2 to the second plus -2 added with 6. Okay? So that's how we did it the old-fashioned way. And let's see what we get. We've got -8. That's going to give us a 4. 4 times -4 is -16 minus 2 plus 6. Okay? So what is this? That's -10. -10 added with -16 is -26. Then -26 added with 6 would give us -20. Okay, so that -20 is the output. Okay? But now the remainder theorem says that we could get the same result, that -20, by performing a synthetic division. So let's redo it. Redo. Okay? So when I now plug in -2 into my function, that -2 in the parentheses is now taking the role of the r in red. So if I want f of -2, that's equal to the remainder of f of x divided by x minus a negative 2. Okay? So you need to get the answer by performing a synthetic division. Okay? So, if you don't mind, I'm going to erase this top part here. I'm running out of room. And now let me go ahead and perform our synthetic division up on top, because I need to find the remainder of f divided by x minus a negative 2, which really means x plus 2. Okay? So, you're going to use an r value of negative 2 and then perform the synthetic division. Well, here's f. So its coefficients are 1, negative 4, 1, and 6. Okay? And now, perform the division. Multiply diagonally, add vertically. Multiply diagonally, I get 12, add vertically. Multiply diagonally, I get negative 26. And what do you know? Look what we're getting. That synthetic division produced a remainder of negative 20. That remainder of negative 20 is what we were looking for. Okay, so f of negative 2, the remainder of f of x divided by x plus 2 is negative 20. Okay? And as you see with the problems that are coming up later, this is going to be beneficial, okay, to get function values by synthetic division rather than the good old-fashioned way. Okay? All right, let's do one more. Let's say part C, let's say part C down below, I'm going to ask you to find f of, let's say, negative 1. Okay? So, if I plug in negative 1, that means that it's now going into here. And now that negative 1 is going to go over here. Okay? So we need to perform a synthetic division now with negative 1. And so our coefficients are the same. 1, negative 4, 1, and 6. Okay? So again, understand that this synthetic division is a very streamlined way of representing our f of x, which was this polynomial here. And merely by writing negative 1, I'm able to represent the polynomial x plus 1. Okay? So now, do the synthetic division. Multiply diagonally. Add vertically. Multiply diagonally. Add vertically. And look what we get. We get a remainder of 0. And that remainder is actually equal to what we were looking for. And that is the function value f of negative 1. Okay? So here we have it. F of negative 1 is 0. Okay? And going back to what we had over here, this remainder of negative 20 was equal to f evaluated at negative 2. Okay? So, watch the follow-up video to this one. It'll be a video on what is called the factor theorem. So, what is the significance of when you get 0 as a remainder in this process here? All right?